Oh my goodness.
What molarity of what?
Acetic acid.
Okay.
I need my glasses.
I love alcohol.
Oh, it's okay. I'm just wondering. I think it's okay. Excuse me.
No. You're not excused. Blame it on whatever you want.
Oh.
So what effect does the structure of the acetate ion have to do with this problem?
Oh.
Nothing.
Yeah.
The only thing that matters is that as long as you know that means it's got one H.
Yeah.
That's the only thing you need to know. And how do we know it only has one H? I mean, I guess we could look up what the acetate ion is, but how do we know it's only got one H if we didn't know anything about acetate ion?
Open pray.
There's only one pKa,
Oh yeah.
right? If it had two H's, there'd be a pKa1 and a pKa2.
Mm-hmm.
All right, so if you know how to do this, this is pretty simple, right? So I'm just going to call it that because I really don't care about the formula of acetate right now. So we're going to get AC minus plus H3O plus, right? So I have no idea what I start with. I do know those start at 0. Hold it. But I know it's got a pH of 3. And if that, it breaks up into 1 and 1, so this has also got to be that. Oh look, I got all my numbers. So 10 to the minus 4.74 equals 10 to the minus third squared over x minus 10 to the minus third. Let's try to drop that. Make our life a little easier. And we end up with an x of,
I got 0.05.
it's 10 to the minus 1.26. I don't know what that is, but I mean, I could do like simple addition and subtraction things, right?
Yeah.
So x is equal to 10 to the minus 6 over 10 to the minus 4.74. So 6, when you divide, you subtract exponents. So negative 6 minus minus 4.74 is 1.26.
It's 0.055.
Yes?
Where did the x's go in the products? You just get rid of them?
The x's in the products. I know what the pH is. I know that number. And I know it started at 0, so this value, the amount that breaks up, is not unknown. I know how much it is.
Well, then why is the x in the reactor?
Because what I don't know is what molarity I started with. See? This is what I don't know. What molarity will give you that pH? And so in this case, the x is over here because I don't know what molarity will give me a pH of 3. Okay, let's extend that problem. What molarity of sodium acetate must you add to this solution from the first problem to give us pH 5?
Yes.
Doesn't that mean you have to like count the acid that's formed as a result of the reverse reaction?
So what do we know about sodium acetate? What do we know about sodium acetate?
It's
It is probably a base. It's
Yeah.
basic, but what do we know about it as far as this problem goes?
what's the conjugate base?
It contains the conjugate. Base.
Well, yeah.
The first crucial thing to know is that it's attached to sodium, which means it's a strong electrolyte.
Yes.
Yeah, so that'll be long.
Okay, that's the first important piece of information. It's a strong electrolyte, which means what? What does strong mean?
Breaks
Breaks
up.
up.
Totally breaks up. So as far as we're concerned, it's X molarity sodium, X molarity acetate. Sodium is the conjugate acid of the strong base sodium hydroxide, which means it's irrelevant. Because remember, the conjugates of strong acids and bases do not affect pH.
Mhm.
Okay, so we don't have to worry about the sodium. We can just kind of go, yeah, whatever, it's got sodium. All right? That should be enough to get you to the end of the problem. Let's see if that does. Okay, so I've got the same reaction going on, except now I know what my acetic acid is because we just found that. However, the question is, how much sodium acetate do I need? There's my X. And it's to give us, so how much of the acetic acid broke up? I know how much broke up. How much broke up?
10 to the negative third.
10 to the negative fifth, right?
Yeah.
Because I know this number right here is 10 to the minus fifth.
Yeah.
Because it's, well, it's over here, pH 5, right? So because I know that, that means I know this. And I know there's a 1-to-1 ratio here, so that's got to be 10 to the minus 5 also. So this is x minus 10 to the minus 5. And this is minus 10 to the minus 5. So this is 0.055 minus 10 to the minus 5. So let's go through the failure points on this problem. Failure point number 1. Recognize that that's a strong electrolyte. Failure point number 2. recognize that is the conjugate base of the acetic acid, which means it's talking about this. Failure point number 3, trying to put a separate reaction of what's going on with sodium acetate in water. It's not. Sodium acetate is influencing this reaction. So we don't have a separate reaction for what sodium acetate is doing because it's a strong electrolyte. It just, as far as we're concerned, it breaks totally up and I've got sodium and acetate and I don't care. Okay. All right, so let's see what we have here. So 10 to the minus 4.74, still have that, is equal to x minus 10 to the minus 5 times 10 to the minus 5 over 0.055 minus 10 to the minus 5.
What would be x plus 10 minus 5?
Let's simplify. If x is small relative to 10 to the minus 5, then I can get rid of these. I don't think that's going to work, but we'll try. I don't think it's, yeah.
Why is on the product side, is it minus 10.5?
Oh, I don't know, because I was an idiot, I did it wrong. It should be plus, right, it's product. Sorry. Okay. Okay, well, let's see if it works. So what do we get for x? I may not get to drop that one, we'll find out. I should find out. Not that it makes it a quadratic or anything, so it's not like it adds any difficulty to the problem, but you know.
Zero point one.
0.1?
Yeah. And that's the same as if you didn't drop it.
So is that small, is 10 to the minus 5th small relative to 0.1?
Yes.
So that was legitimate. Okay, so good enough. So we can check our work. 10 to the minus 4.74 equals 0.1 times 10 to the minus 5 over 0.055. Do these sides, does that equal 10 to the minus 4.74?
That's about it.
I mean, is that a true statement?
Yeah, looks like it.
Cool.
Yeah.
Plus or minus significant figures and
Yeah.
stuff like that, you know.
It's accurate. Okay.
All right.
Yeah.
Are you getting the hang of this? Now, what if it was, what if I had a problem? Well, let's just do it. Here we go. I'll just give you another one. Do another problem, make sure we're all on the same page here. You need to be pretty comfortable with this before we go on. Just a second, let me go back here to the back. And find some. Yeah. And before you waste time on Google, I don't know what the formula of adipic is, don't really care. Okay, so whatever. I just pulled it out of the textbook there and it said adipic acid gave you some K's. So that's good. What do you know about adipic acid? It's got 2 hydrogens on it. That's what we know. That's the only important thing. It's got 2 hydrogens attached to adipate, I guess. I guess that's what it is. Okay, so. But from an acid-base standpoint, I don't really care. Now, I have all these people talking about biology. Okay, over here in biology, we care because for all I know, adipate is some horrible poison that's going to kill us all. You know, but it won't be the acid and base that does it. It'll be something else. Remember that H is coming forward the time, right? That's why we have 2 K's, because the H is coming forward. So I have H2 adipic acid. I don't know, I'm just gonna call it AD because it doesn't matter. I actually have the formula, not that it matters. C6H8O4, I don't know, whatever that is. Okay, so H2AD is gonna react with water to give us HAD minus plus H3O plus. Okay? And then we just do our normal, 0.25 minus x, 0, 0, x, x, right? So 3.9 times 10 to the minus 5th equals x squared over 0.25 minus x. Let's try to drop that. So if x is much less than 0.25, we can drop it. And when we solve for x, we get, I saw 3.1 times 10 to the minus 3rd back there. What you got? That? Okay.
Yeah, that's right.
Okay. What do I do with that?
Negative log.
I don't go on to Ka2. Because remember what we talked about last week? Ka1 determines pH. Because Ka1 is bigger than Ka2, and remember, only the strongest acid determines the pH. Ka1 is stronger than Ka2, therefore it determines the pH. So, the pH is 2.5, something like that, 2.6?
Yeah, 2.5.
2.5. So the pH is 2.5. Because remember, this reaction right here by adding this into here, that raises this value, and Le Chatelier says this reaction is being shifted towards reactants. And so this is going to be a trivial amount of extra H3O plus because, according to Le Chatelier, it all gets shifted back to reactants. Okay? So we had a very small incremental addition to that number, which is basically it. Okay? If we actually worked it out, you'd probably have to go to the 4th or 5th decimal place of the pH before you found a difference in the number. Be like 2.50001 or something like that. So, not gonna make a difference. All right. So, if you've got a polyvalent ion, a polyprotic acid, the pH is from Ka1. The only time I would need to know Ka2 and Ka3 is if I need to know the ions that come from the 2nd or 3rd ionization. So, for example, in boric acid, H3BO3. If I wanted to know what's the free borate ion concentration, now I would have to do Ka1, Ka2, and Ka3 before I actually got down to BO3 minus 3. Yes, ma'am?
Will we have to know how to do that for the test?
How to do it? Sure.
Like, will we have to do it though?
I don't know. I don't know what question I'm going to ask on the test yet. I haven't got there. However, if I ask you to do the free borate concentration on H3BO3, for example, then I have to not ask you a bunch of other questions because I just basically asked you a question that's 3 times longer than what's the pH. So basically, to ask you that question, I have to take 2 other questions off the test. Not saying I won't, but I'm just saying the test gets shorter if I do.
It's not necessary.
I'm good with that.
However,
Easy.
I would not put it all past me to say, okay, what's the pH of this? And let
then
you
you
waste
can-
time finding out what Ka2 was,
Yeah.
which you didn't need to do, right? That sounds like something I would do.
Okay.
Okay. Now, if we go back to, let's just say I've got some sodium adiptate here. Oops. Sodium hydrogen adiptate. Got that right here. So say we have this compound right here. So let's ask that question. How much sodium hydrogen adiptate do I need to add to this equation to get a pH 5? What do we know about sodium hydrogen adiptate?
It's a strong electrolyte.
It's got to be a strong electrolyte because it's got sodium on it, right?
Yeah.
If it has the conjugate acid or base of a strong acid or base, then it's a strong electrolyte. Okay? Okay. How did we do it last time?
Oh.
How did we do it last time? It's the same question.
Oh.
So since it's a strong electrolyte, that means the concentration of this is equal to the concentration of sodium, which I don't care about, and the concentration of that, right? That's what it means to be a strong electrolyte. It all breaks up. You should be seeing a distinct similarity because this is almost exactly the same problem we just did a minute ago, right? Okay, but now I don't know how much of that I have to start with because it's asking me how much do I need. But I know I need it to be pH 5. So this has got to be plus 10 to the minus 5, plus 10 to the minus 5. Minus 10 to the minus 5. Right? Looks to me like about 0.95 molarity, something like that.
97.
Huh?
97.
9.7. Okay. That is definitely really small. 10 to the minus 5. Oh no, hold it. Ah. There we go. Because it's got to be smaller than the X to drop out, not X smaller than X. Okay. Whoops. Oh yeah, I did. All right. Okay. Do you guys see that this is exactly like that original problem I did with the acetic acid and the sodium acetate, right? Same problem. Yet some of you guys were still struggling. You need to be able to recognize I changed the chemicals. It doesn't change what's going on. It's still, I'm adding a product. What happens? Right? Okay. This that dissociation right there, that's technically what's going on. It's a strong electrolyte, so we start with some of this, it all goes away, we have 0 of that left over, right? And then we get whatever of those. What I want to show you is this. The reason why we're able to mix and match these is because we have a common ion, okay? So these two reactions have a common ion. So for example, let's try this. What is the effect on pH of adding 1.2 molar NaCl? So I add a bunch of salt. When NaCl breaks up, what do we get?
NaCl.
We get NaCl. Do we have common ion
Yeah.
between my H2AD
No.
lactic acid and my
No.
sodium chloride?
No.
So what's the effect on the pH?
None.
Nothing.
None, because there's no common ion. If you don't have a common ion, then you are not having an effect. Good. That is even called the common ion effect. Because you have a common ion, therefore you affect the other reaction. Okay. Next thing I want to talk about are titrations. Okay, so let's talk about titrations a little bit. So, how much 0.15 molar NaOH titrate 200 mils of 0.25 molar dipic acid. I'm gonna have to go look up adipic acid. I've been using it so much here today. No idea what adipic acid is. My guess is it's a bile salt. That's what I'm thinking. Kind of sounds like a bile salt. So when you say you've titrated something, typically you titrate it to where? What do we call when we're done with a titration? What do we call that in lab? You know what we call that in lab? Remember? What's the point where the reaction ends?
The end.
The end point?
Yeah.
Oh, yeah. Okay, so we go to the end point of the reaction,
Wow.
which would be where, what's in my beaker when I get to the end point? How much adipic acid's left in my beaker when I get to the end point?
None.
None, because I'm at the end point. And I don't have any sodium hydroxide either. It's where all of my reactants are used up. That's what an endpoint is. Endpoint is where you only have products, you do not have any reactants left. In Chem 1 terms, both of them are the limiting reactant. They're both gone. Okay? So I go from sodium hydroxide being the limiting reactant when all I have is adipic acid in my beaker, to neither one of them being the limiting reactant. Okay. So let's see if you've forgotten absolutely everything from Chem 1. Here we go.
I certainly have.
It's kind of a Chem 1 problem. As a matter of fact, we did that on Friday in Chem 1. So I know it's a Chem 1 problem because we did it in Chem 1 on Friday. Okay, so can you do it? Do you remember anything from Chem 1? There you go.
Oh shoot, it's a.
M1D1, yes, M2D2. Oh, duh.
You're welcome.
Yeah, no.
5 years ago.
Wait, why would we need the dilution formula? Don't we need the moles to get the limiting reactant?
Yeah.
No, I just know there's an equation that has this.
So yeah, we just.
So we're writing a reaction and the word limiting reactant got put in there. So what does that sound like we need to write to start off with?
A balanced equation.
There you go. A balanced equation would be awesome. Can we write a balanced equation for the reaction of sodium hydroxide and adipic acid, realizing once again that whatever adiptate means is still irrelevant? Okay, can we do that?
Yeah.
Hopefully.
We have the power.
You have the power. You can do it. NaOH is going to react with H2 adiptate, whatever that is, to give me Na2 addict, whatever that's called, and looks like 2 waters. Looks like I need 2 of those.
That was 2.
Right? Okay. So, after you, I'm sorry, what? The 2 what? This? Because there's 2 H's on that, so that's got a -2 charge. This is +1, that's gonna be a -2, so that's a -2, that's a +1, I need 2 of them. Right? Okay. Okay, Chem 1 again. Okay, so let's go through the steps. First step, write a balanced equation. Okay, we did that.
Yeah.
Although some of you need some help. Okay,
Yeah.
so we did that. Now what are we going to do? What do we do? After we write a balanced equation, then we always...
I don't think we would destroy anything.
anything. We're just doing any old chemical reaction. You balance it, then what do?
You get the moles of
Get the moles. You find the moles. Right? First thing you do, because chemical equations are number ratios. Right? So the first thing you do is get a balanced equation so you know what the heck you're talking about. Right? Because if I think you're talking about turkeys and you're really talking about jelly beans, that's a different conversation. Okay? So we got to make sure we're really all talking about the same thing. So we got to have a balanced equation.
Yeah.
Then we needed number ratios. So we needed moles. That's our way to turn a number into mass into a number, right? That's how we do that. Okay, can we find the moles?
Yes.
Cool. Oh, hold it. Oh, whew. It's in molarity. I don't have to ever go figure out what the heck adipic acid is. Awesome. Okay, that's good. Guys, what's molarity? Definition? Moles per liter. Awesome. Somebody else has already figured out the molecular weight of adipic acid. I don't have to. Okay, that's good. Okay, so as long as we trust whoever made this stuff that they actually went and looked the formula up so they knew what it was. So, awesome. So how many moles of adipic acid do I have? 0.25 moles per liter. That's what 0.25 molarity is. So how many moles if I have 0.2 liters?
0.05.
The ratio, right? Okay, I got 0.05 moles.
That's crazy.
And I know I'm at the end point, so I used them all up. Well, how many moles of sodium hydroxide do I need to use up all of that?
1 for 1.
Yeah.
0.1,
Well,
right? I need a 2-to-1 ratio.
These 2 times 1. Or no. Yeah.
I'm at the end point because I don't have any reactants left. That is the definition of the end point. Is that the question? What's the question? How many mils of sodium hydroxide? Can you find that now?
Yeah. Pretty easily. That did it. That did it so good.
No.
Yeah, it's the whole thing.
Okay. Well, maybe. Who knows? That might be. I don't know. So I have 0.15 moles per 1 liter. I need 0.10 moles. Oh, looky there. I'm going to get 2/3. Okay, so X liters. So X equals 0.67 liters. Okay, that's how you do it. Anytime you do titration, write the equation, set the moles to where all the reactant moles are gone, and then go from there. Okay? Okay? Not sure some of you are ready for it, but let's try a harder one. Okay? So let's do one that's a little more challenging. What the heck? Well, no, let's do oh, what the heck? We'll stay with it. You guys have the KAs still written in your notes, right? So I don't have to write those again. Okay, so what is the pH of 0.25 molar adipic acid? Oops.
Oh, it was like 3.9 times
200 mils of 0.25 molar adipic acid after titrating in 200 mils of 0.15. Yes.
I don't understand the cross
Molarity is moles per liter, right? And so it's moles per liter on both sides of the equation.
Right, but why is it 0.15 over 1, 0.1 over x?
0.15x equals 0.1, right, when I cross multiply? 0.15, if I cross multiply that fraction, I get 0.15x equals 0.1.
Yes.
Then I divide both sides by 0.1 to get x by itself, and I end up with 0.1 over 0.15,
Yes.
which is 2/3.
I understand how to do it, I don't understand why the numbers are where they are. Like, why is it 0.15, why is it 0.1?
Because the molarity of the stuff is 0.15 molarity, which is by definition 0.15 moles per liter. Right, you're given that, that's in the problem. We know we need 0.1 moles because that's what gets us to 0 in the reactant side. And so that goes on the other side of the molarity fraction. Does that make sense now? Okay, so I need to find the pH, so I need to go back to my original adipic acid equation.
Why is that first? I thought you tried to get rid of it first.
And then this,
Which fully dissociates.
does that share a common ion? Those two reactions?
No.
No, they don't. They don't share a common ion, but
Strong acid. Or strong base.
Wait, acid base, you add them together. You get-
I have OH,
Which neutralizes H3O.
right?
Yeah.
So the OH is going to get in there and react with the H3O plus. What's that going to do to my reaction? What's that going to do to it? According to Le Chatelier, what happens when I add the OH to this reaction?
Oh, we can go forward.
Can you see that I'm essentially removing H3O plus?
Yeah.
That's what I'm doing, right?
Uh-huh.
And so I'm shifting the reaction towards products
Yeah.
as I try to get rid of that OH.
Uh-huh.
And remember, the H3O, the H2O goes to H3O plus OH minus, that's KW, right? Remember, KW is 1 times 10 to the minus 14th, which means essentially this reaction would be 1 over 10 to the minus 14th, which would be what, 10 to the 14th, right? So this reaction absolutely goes to completion, essentially. So I remove this. So I start with 0.05 moles. And this is 0.03 moles.
Yeah.
So I have 0.02 moles left. This essentially all goes away because, yes, right? So I have 0.03 moles of that because I have it from over here. And I would have 0.03 moles of this, but this went away. It's gone. That extra is gone. So when this goes away, all I have left is X. So basically what happens is this. Let's see if I can explain this. You start with 0.05 moles of reactant, and you react 0.03 moles of it. So I got 0.02 moles left. Yeah, 0.02 moles left, right? So I have 0.03 moles of my two products. But the 0.03 moles of H3O plus went away because I reacted with OH. That does not influence the HAD. That's still there. But it does reduce this down to 0. Now it tries to re-equilibrate again. And so I'm going to add X more as X more of this tries to break up. Matter of fact, let's just do it that way. Let's just call this 0. I'll do it this way. And now that's my initial. Does that help doing it that way? What?
Where'd you get 0.0?
This number?
Yeah.
Where'd I get that? Right here. 0.15 moles per 1 liter equals X over 0.2 liters. X equals 0.03. Right there, 200 mils of that. Right? So I have 200 mils of this. How many moles is in that? So 3.9 times 10 to the minus fifth equals 0.03 plus X times X over 0.02 minus X. If X is really small relative to 0.02, that's going to cancel those out.
Yeah.
And so X equals 2/3 of 3 times 10 to the 9 times 10 to the minus 5, whatever that number is. 2.4, 2.5, 2.6.
2.6.
2.6 times 10 to the minus 5th, which is the H3O plus. So my pH is 4.6.
Yeah, 4.6.
So this is what happens when you do a partial titration. So on Wednesday, we'll go through and do a titration, and we'll figure out what the pH is after 10 mils, after 20 mils, after 50 mils, after 100 mils. And it should probably, I mean, by the time we get done with that, probably be like, okay, I get it already. Let's quit doing this. Okay. But we'll try it again on Wednesday, see if we can get you guys up to speed on this. Okay?
Yeah.
Cool. See you Wednesday.
Alright, what's tricky here?
I don't know.